Welcome to CS 320, where we're going to finish the proof of Kleene theorem. We proved almost all of it except for this very last part, which says that if we have a regular expression, we can star it. And so what we need to do is take any finite automata. So we need to prove that any finite automata can be starred. So that means is we take a finite automata, it accepts some words. We need to create a new finite automata that accepts all of those words repeatedly, so we can have lots of them, or we can have 0 of them. So the best way to learn how to do this is by an example. So now what we have here is a finite automata for this regular expression. Now it's not really important what this language is, but we will look at it. This language is a language of all A's, or any word that ends with a B and only one B. So we can have all A's or A's and end with a B. And here is a finite automata that accepts the same language, and any word that does not end in a B moves down to this state, and we need to basically read the rest of the letters in that state. Okay, so the reason why we chose this language is some languages like even, if you star that, it actually doesn't change the language. Because you take a word with an even number of letters and you repeat it, you're always still going to have an even number of A's and B's. So the language even isn't really a good example. But in this case, if we do star this language right here, that means that we can have more than one B, whereas right now we can only have one B. So the resulting language is going to be different than the original. Now, if we star the regular expression, we also have to be able to star the finite automata. And now I'm going to review the step-by-step procedure that we'll follow that will star any finite automata. Now you can read the step-by-steps, the algorithm in your book, but I'm just going to do this demonstration. So we're going to start off with a start state labeled with an x1, and we'll continue for there. And now you can see if we're in x1 and we read an A, we go to state x2. Now, one thing with this state x2, if you notice, it's a final state. So we could have read one word from our language, and we could start on the next iteration of this finite automata, or we could continue on with reading the first word. So we kind of have that choice there. How we're going to represent that choice is by putting the label x1 inside of that state. So the rule is whenever you land in a final state, a final state in your finite automata, you put x1 in that state as well. Now, if you notice, this is a final state. This is a final state as well, but it already has x1 in it. So let's keep going. If we're in x1 and we get a B, we go to state x4. Okay. Now, if we're in state x2 and we get an A, we stay in x2. If we're in state x1 and we get an A, we go to state x2. And but x2 happens to be a final state, so we also need to include x1 in this state. And if you notice, this is the same state as that, so really this just loops back to itself. And now if I'm in state x2 and I get a B, I go to state x3. If I'm in state x1 and I get a B, I go to state x4, but also x3 happens to be a final state, so that means I can transition and start this all over again and go to state x1. So that will be a new state that we've gone to. And now let's do state x4, and x4 is actually going to be pretty easy. X4 is going to be pretty easy because A's and B's are just going to go back to X4. and they're not going to go to another start state or anything like that. Okay, now let's try this state again. If we're in state x3 and I read an A or a B, I go to state x4. So we'll just do A first. If I read an A, I go to x4. If I'm in state x4, I read an A, I go back to x4, but that's already there. If I'm in state x1 and I read an A, I go to state x2. Now, x2 also happens to be a final state, which means that I could be in state x1. And I don't see that state anywhere, so I'm going to keep that state. And now we'll go ahead and do the B edge. If I'm in state x3 and I read a B, I go to state x4. If I'm in state x4 and I read a B, I stay in x4. And if I'm in state x1 and I read a B, I go to state x4. So in this case, a B, I just go, no matter what, I go to that state right there. Let's do this state right here. If I'm in state x4 and I read an A, I go back to state x4. If I'm in state x2 and I read an A, I stay back in state x2. x2 happens to be a final state, so that includes x1 on it. And if I'm in state x1 and I read an A, I go to state x2, which is that state. And this state is the same as this state, so we'll just loop back. Okay, now we'll do the B edge. If I'm in state x4 and I read a B, I go to state x4. If I'm in state x2, I read a B, I go to state x3. x3 is a final state, so that also includes x1. And if I'm in state x1 and I read a B, I go to state x4, which is already there. So x4, x3, x1, that happens to be this state right here. So a B, we'll just go back that way. And now we've done all A and B edges. And if you're worried that this is going to go on and on forever, if you've studied the concept of a power set, the number of states we'll have will just be a power set of all these states. And since this is a finite number of states, we'll definitely have our output be a finite number of states as well. Now, the last step is to figure out our final state. So anytime we land in a final state of the original machine, so that's state x1, x2, or x3, that also means that we'll be in a final state. So this x2 is a final state. This x1 will also be a final state. x3 is a final state, so it'll be a final state here. And x2 is a final state, so this one will be a final state. In fact, all of them are a final state except for this very first one, state right here. And that is if I read a B at the very beginning, or I read two B's in a row, which is not allowed according to this finite automata, then that throws me into this state right here. And so that's our one rejection state. Everything else is a word in the language. So it's actually not a bad finite automata for this regular expression. Now we're going to do one more example of this to make sure we got it and to show some situations that might happen in certain cases. Now let's try it with this finite automata. This finite automata accepts all words that end in an A. Now, one little note, if we take all words that end in an A and restar it, we still just have all words that end in an A. But let's see what this algorithm does to this machine. So we'll start off with a state for x1, and that will be our start state. And if we read a B, we just go back to state x1. So if we're in x1 and we read a B, we just go back there. And if we read an A in x1, we go to x2. Okay, and since x2 is also a final state, that means that we can either keep reading a word from the first iteration of the star, or we can transition and start reading a word from the second repetition of the word. And so that means we need to put x1 in here. Now let's continue. If I'm in x2 and I read in A, I stay in x2. If I'm in x1 and I read in A, I stay in x2 as well, but x2 is a final state, so I also have to include x1. So that means that we just add this edge. Now, once again, an A in x2 goes back to itself, and A in x1 goes back to itself. And we did that because we have both x2 and x1 inside of here. But x2 is a final state, so that's why we keep x1 in that state. Okay, let's keep going. If I read a B in x2, I go to x1. If I read a B in x1, I go back to x1. So that's this state right here. Okay, and now we'll just include the final state is any state that includes x2, and that's only this state right here, so that will be our final state. And if you notice, the finite automata did not change at all. But when we star something, that means that we can have 0 or more words. And the null word is not in this language. But when we star it, the null word should be in this language, but it isn't. So what are we going to do in that case? So in the case that we have a loop or an edge coming back into the start state, that means, if I were to go ahead and add the null word in, or add this as a final state, I'd now change the language because now I accept all words. So I can't do that. And you can't do that if you have edges coming back into it. So on the previous example, we had no edges coming back into the start state. So what we need to do instead is create a new start state. And we're going to pretend like this state is this state right here. And if we're in this state and we read an A, we go to that state. And if we're in this state and we read a B, we go to that state. And now we can make this a start state and a final state and not have this be a start state anymore. So now this language here accepts the null word and any word that ends in an A. So that is this starred. So you have to make, whenever you star a word, you have to make the start state a final state. But we can't make this state a final state, or else we add more words in the language that shouldn't be in there. So if the start state has arrows coming into it, then we need to create a new start state that can be a final state. And it just does the same thing that this state does. So a B goes to here, and an A goes to here. So the edges leaving go to the same spot that the edges leaving this state went to. And that is the complete algorithm to start a finite automata. And now we have proved Kleene theorem. And we know that if we can define a language using a finite automata, a regular expression, or a transition graph, we can also define them using the other methods. So thanks for watching.